One reason it's important to know about exponential functions and logarithmic functions is because there are a few phenomena in the world that are actually described by exponential functions, at least for certain practical purposes. Here's one example. So let's say we have a bacteria culture that contains 100 cells, and the cells are reproducing so that the number of cells doubles every hour. Let's find a function, p of t, for the population of the bacteria culture after t hours. So let's start just by making a chart. Okay, so let's keep track of how many hours has elapsed, that's t, and the population of the cell culture after t hours. So after 0 hours, that is at the beginning, there are 100. After 1 hour, that's doubled because the population doubles every hour, so now it's 200. So to get from line 0 to line 1, we just multiplied by 2. After 2 hours, it doubles again, so now it's 400 cells. And to get from line number 1 to line number 2, we multiplied by 2 again. And let's do one more line. After 3 hours, we double again, so now there are 800 cells. And to get from line 2 to line 3, we multiplied by 2. Well, what we really want is to know what would go down on line t in this table. So what we need to do is look for a pattern here. Well, if you look at each line, these all start with, or these all have something to do with, the 100 cells that you start with. So at the beginning, it's the 100 cells that you start with. Here, after 1 hour, it's the 100 cells that you start with, but then multiplied by 2. After 2 hours, it's the 100 cells that you start with, but then multiplied by 4. And after 3 hours, it's the 100 cells that you start with, but multiplied by 8. So thinking of t being 0, 1, 2, and 3, we get these multiples. I guess even at times 0, there's a times 1 right here. So thinking of the time being 0, 1, 2, or 3, the multiples in front are 1, 2, 4, and 8. Well, these should look familiar. These are just the powers of 2. 1 is 2 to the 0th power. 2 is 2 to the 1st power. 4 is 2 to the 2nd power. And 8, that's 2 to the 3rd power. But we've seen this kind of pattern before. This is the pattern where the exponent number matches the row number. Here the exponent number matches the row number. The exponent number matches the row number. And we've seen that in this situation, you always get an exponential function. So we know that p of t is some exponential function. So let's write a times b to the t. To figure out the unknown constants, a and b, as usual, we just need some data points. But look, we have a table full of data points. Our initial value when t is 0 is 100 because we started with 100 cells. And if you plug t equals 0 into our formula for p of t, you get a times b to the 0, but that's just a. So now we know a. A is 100. Now let's plug in the data point for after 1 hour. So p of 1, according to the table, should be 200. And if we plug t equals 1 into our formula so far up here for our function p, well, we already know a, that's 100, times b to the 1st power. So now we know b. b is 200. And this means that our function, p of t, is a, which is 100, times b, which is, sorry, I made a horrible mistake here. b isn't 200. We need to divide both sides by 100 here. That cancels some of these zeros, and b is 2. That's more like it. So p of t is 100 times 2 to the t. And you can see that this situation where a population doubles every period of time, it produces this exponential function. And really, the characteristic thing about this situation that forced there to make an exponential function is this doubling. If you're in any situation where moving from one to the next, you multiply by a constant, and in this case, for moving from one row to the next, we're multiplying by 2, that always produces an exponential function. All right, let's look at another example. So when visiting a remote island, you accidentally introduce 10 rabbits, and 3 years later, you revisit the island and estimate that there are now 80 rabbits. How many rabbits will there be after t years? All right, so in this sort of situation where you have a population that is relatively unconstrained, this is often modeled using an exponential function for exactly the reason that we saw in the previous example. So we're going to use an exponential function to describe the growth of the rabbit population on this island. So let's call it, I don't know, how about p of t? And we'll say a times b to the t. Right? We know we start with 10 rabbits, so p of 0 is 10, and that's a times b to the 0. But a times b to the 0, again, that's just a. So now we know a is 10. The other data point that we have, it's 3 years later, and it's 80 rabbits. So this is going to be p of 3, and that's 80. And that should be a, but we know that a is 10 times b to the t, but t is 3, because we're plugging in 3 right here. Right, and now we can solve this for b. So start out by dividing both sides by 10. Up here, we get 8 equals b cubed. And now we can take square roots. Not square roots, how about cubed roots? Just to isolate b. And we get, oh, we got 2 again. So our population function this time was 10 times 2 to the t. Okay. So far we've written all our exponential functions in this form as a times b to the t. But there's another way you can write any exponential function, and that is in the form a times e to the rt. So you always have a choice. You can either let the base be anything, but the exponent has to be just t, or you can always have the base be e, but the exponent might have a constant multiple in it, which I've called r here. You can use either one, and you can go from one to the other, but different groups of people have different conventions. So often you'll see exponential functions written with the base always being e, and there being some number in the exponent multiplying time. Just to see how you can go from one to the other, let's turn our population function, 10 times 2 to the t, into this other form that has e for the base. To do that, we just need to figure out, or we need to somehow replace 2, this 2 that is the old base for our exponential, replace it with something base e that's equal to it. And the way to do that, it's just a little algebra trick. It's e to, we need to put some exponent up here so that e to this power is 2. But we already have a name for that. That's natural log of 2. So let me write this a little bigger. So we get 10 times e to the natural log of 2 times, and then to the t power. Well, now we can just do a little trick with exponents. Remember, when you have a base to a power to another power, in parentheses, the exponents multiply. So this is e to the natural log 2 times t. If you want to, you can grab a calculator to calculate natural log 2. It's about 6.9. And so 10 times 2 to the t is actually the same thing as 10 times e to the 0.69 times t. This number here, the constant multiple in your exponent, this sometimes gets called the rate constant. Or time constant, or growth rate, or many other terms. Okay, let's look at one more example of a situation where exponential functions show up sort of on their own. So let's suppose that we have a 5 kilogram sample of radioactive material, and after 20 days that 5 kilograms decays to 4 kilograms. So radioactive material, it sort of breaks down into component pieces in such a way that some of the original mass either is emitted in the form of various types of particles, and the material that is remaining isn't the element that it started in. It actually turns into something else. And one characteristic thing about radioactive decay is that it's exponential. So let's find an exponential model for the mass of material remaining after t days. Just for a little variety in this example, let's find our mass function m of t. Let's write it using this exponential formula that always has e in the base. So we're going to use a times e to the rt. And remember, the unknown constants in this are a and r. All right, well, we need to find these unknown constants so that we know what the mass function is, but we have a couple data points. We're starting with 5 kilograms, so that means m of 0 is 5, and we have 4 kilograms after 20 days. That means m of 20 is 4. Okay, well, we have a formula for our exponential function, so we can plug our t values into here. For the initial t value, we get a times e to the r times t is 0 for this one, and e to the r times 0 is 1, so this is just a. So now we know a is 5. For our second data point, we get a, which now we know is 5, times e to the r times 20. Okay, so the second data point turns into the equation 4 equals 5 times e to the 20r. And now we need to find r. Well, when you have an equation where the variable is trapped inside of an exponent, you're going to have to use a log to solve that equation. But before we use a log immediately, we should isolate the part of the equation that has the exponential. So let's start by dividing both sides by 5. So we get 4/5 is equal to e to the 20r. Now we're in a position to take logs. So let's take logarithm on both sides. And it's going to be a natural log since the exponential is base e. On the left-hand side, we get natural log of 4/5. And on the right-hand side, natural log of e to something is just the something, so that's 20r. And now we can divide both sides by 20. And finally, we know r. R is natural log of 4/5 over 20. And if you like, you can find a decimal approximation for this. So natural log of 0.8 divided by 20, I get negative 0.0112. It's actually 1115 and then some more digits, but let's just round it to the fourth decimal place. All right, so that means our mass function, m of t, is 5 times e to the negative 0.0112 times t. Now it might worry you that this rate constant r came out to be negative, but that is actually a sign that, so this negative here is a sign that the mass is decreasing. Remember, exponential functions come in two varieties. There are the exponential functions that increase, and there are the exponential functions that decrease. Well, since in radioactive decay, the mass of the sample is decreasing, it must look like the second one. But for the second one, that's the decreasing exponential function. Those are exponential functions where that rate constant is negative. So we shouldn't be surprised to have gotten a minus sign there. Okay, so finally we know the mass function. Now let's answer the second part of the question. How long will it be until half of the sample has decayed away? Okay. So let's see. If we started with 5 kilograms, then half of that is 5/2 kilograms, or 2.5. So we want to know, when does the mass get down to 5/2? To know when that happens, we can just take our mass function, m of t, set it equal to 5/2, and then solve for t. So this is 5/2 equals m of t, but m of t was 5 times e to the negative 0.0112 times t. So we just need to solve this equation. But this equation has the variable in the exponent. And when you have an equation where the variable is in the exponent, you're going to use a logarithm at some point. But before we take a log, let's isolate the exponential part. So we can divide both sides by 5. On the left-hand side, be a little careful with the fractions there. 5/2 divided by 5 is 1/2 equals e to the negative 0.0112t. Now we're ready to take logarithms. But before we do, just let me point out that it actually didn't matter what mass we started with. Whatever mass we started with, once we isolated the exponential part, we would have ended up with a 1/2 on the left here. So this 1/2 is always a 1/2 right here when we're looking for half of what we started with. So half of the starting mass. So when we find the time that it takes to get to half of the 5 kilograms, what we're actually finding is the time that it takes for the mass to be half of what it started as, no matter what it started as. Okay, so let's finish solving. Just take a natural log on both sides. On the left-hand side, natural log of 1/2. On the right-hand side, the natural log and the exponential base e undo each other, and you get negative 0.0112 times t. Then divide both sides by negative 0.0112. And we get t is natural log of 1/2 over negative 0.0112. And let's Find an approximation for that. So natural log of a half divided by negative 0.0112, I get 61.89, and this is in days. So it takes our 5 kilogram sample about 62 days to decay into half. But remember, no matter how much we started with, it would take 61 days, about 62 days for this radioactive sample to decay to half its original mass. So this 62 days is called the half-life of this radioactive material, because this is how long it takes for half of the material to decay away. Of course, after a second half-life elapses, then half of the remaining half is what's left over, and so you're left with just a quarter. And after 3 half-lives, you're left with an eighth, and so on.